Hi, I'm Shuichi Hirahara. I'm going to talk about errorless versus error-prone average complexity. This is a joint work with Rahul Santhanam. In the theory of average complexity, we study a distributional problem, which is a pair of a decision problem L and the family of distributions D over instances of L. In the average complexity, we ask the following question. Is the decision problem L easy on average with respect to the distribution D? More specifically, let's say you are given a random input X, which is drawn from the distribution D. Can we decide whether X is in the range L or not with high probability efficiently? When we try to formalize this question, there are at least two ways to formalize average case tractability: errorless or error-prone heuristics. It is often denoted by average P. Errorless is denoted by average P, and error-prone polynomial time algorithm is denoted by Heuri-P. In this work, we initiate the study of the relationship between errorless and error-prone average case complexities. Let me explain the motivation to study this question. There is a very influential paper about average case complexity written by Impagliazzo. He proposed 5 possible worlds that are consistent with our current knowledge on cryptography and complexity theory. For example, pestilence is the worst possible world in which NP is hard on average, but there is no one-way function. Similarly, heuristica is a world where there are efficient heuristics for NP, in the sense that NP is easy on average, but NP is hard in the worst case. Now, in order to formalize these two worlds, we need to decide which notion we should use, errorless or error-prone. Therefore, it's quite natural to ask whether these two notions are equivalent to each other. In fact, this question was explicitly raised by Impagliazzo's original paper. He raised the question of whether distribution NP is in Heuri-P implies distribution NP is in average P. Here, Heuri-P is a class of distribution problem that can be solved by error-prone polynomial time average case algorithms. More specifically, we say that L, D is in Heuri-P if there is a polynomial time algorithm A such that the following holds. A takes some parameter K, which specifies the error probability of the algorithm, and if we pick X from the distribution D, the probability that A fails to compute the correct answer L of X is at most 1 over K. This is the notion of Heuri-P. In contrast to this, average P, which is a class of distribution problems that can be solved by errorless average case polynomial time, we additionally require that the algorithm outputs either the correct answer L of X or a special bottom symbol, which indicates that the algorithm doesn't know the answer. So obviously, this is a stronger notion than Heuri-P. The question Impagliazzo asks is that whether these are equivalent for NP or not. Before explaining our result, let me explain the key insight or the starting point of this paper. Our main starting point is that we find a connection between instant checker and the question of Impagliazzo. Namely, if we have a non-adaptive instant checker for an NP complete problem, we can show that the answer to the Impagliazzo's question is positive. More generally, we can show that the existence of an instant checker gives a reduction from errorless to error-prone average case complexities. For example, if you are not familiar with instant checker, one canonical way to construct instant checker is to consider an interactive proof system. For example, if we have pH, if we can show that pH admits an interactive proof system with a pH honest prover, this is essentially equivalent to having instant checker for pH. In that case, we can show that the average case compressed error-prone average case compressed of pH and errorless average case compressed of pH are equivalent to each other. Currently, what we know about interactive proof system for pH is that pH admits interactive proof system with P to the sharp P computable honest prover. So if we can improve this complexity of honest prover, we can prove the equivalence between two different notions of average case complexity for pH. Now let me introduce three our main results. The first result shows that we can get equivalence in a certain setting. If we consider average case version of an instant checker in a non-uniform setting, we can actually get an exact equivalence. Specifically, we can show that the following equivalent. There is an errorless-to-error-prone reduction showing that errorless complexity of NP and error-prone complexity of NP are equivalent if and only if there is a non-adaptive average BPP/poly instant checker, which is an average case version of instant checker for NP complete problem. One way to interpret this result is that this provides a new approach for errorless-to-error-prone reduction. Actually, it is a long-standing open question to construct a worst-case instant checker for an NP complete problem, which is actually explicitly raised in the seminal work of Blum and Kannan. But in order to construct an errorless-to-error-prone reduction, we showed that average case instant checker is sufficient. So this provides an approach towards errorless-to-error-prone reduction. Moreover, we can show that there is a Heuristics BPP instant checker, which is a weaker notion than average BPP instant checker, but we can construct such an instant checker for NP complete problems unconditionally. The second result is some unconditional result about the equivalence between two average case complexities. We were able to show the equivalence between errorless and error-prone average case complexities for P and UP intersect co-UP. For example, in the case of P, we can show that errorless complexity and error-prone average case complexities are equivalent. For example, in the case of NC1, we can state it in this way. The proof idea is basically quite simple. The reason we can get such an equivalence is that there is an instant checker for P computable problems. By using the connection from instant checker to errorless versus error-prone average case complexities, we can get this equivalence. Similarly, for UP intersect co-UP, we can show a similar result, showing that errorless and error-prone average case complexities are equivalent for UP intersect co-UP. Our final result concerns the difference between polynomial time pseudorandom generator and polynomial time computable hitting set generator. In general, these two notions are not known to be equivalent if we consider polynomial time computable pseudorandom generator or PRGs. But if we consider a pseudo-extending version, we are able to show the equivalence between these two notions. Here we say that G is pseudo-extending if the function Z takes a pseudo Z and it outputs Z at the prefix of the output. Now we can prove the following equivalence. The first statement says that there is a polynomial time computable pseudo-extending hitting set generator with seed length n-1, which is secure against NC1. In general, it's not, even if you have a heating set generator with seed length n-1, it's not known whether you can reduce the seed length in general. But in the case of a seed extending heating set generator, we were able to show that we can reduce the seed length to n to the epsilon for every constant epsilon. The proof is based on the equivalence between heating set generator and pseudorandom generator. Let me explain the key idea of our paper. Namely, I'm going to explain the connection from the instant checker to errorless versus error-prone average case compresses. In order to explain this, let me first recall the notion of instant checker. An oracle machine C is called an instant checker for language L if we have the following two properties. The first condition, which is completeness, says the following. If you are given the correct oracle L, the instant checker, the probability that the instant checker outputs a wrong answer is at most a quarter. This is completeness. The soundness states that for every oracle A, the instant checker, the probability that the instant checker outputs a wrong answer is at most a quarter. Here, the instant checker is allowed to output the special bottom symbol, which indicates the failure of the computation. So in some sense, this is an errorless. This is quite similar to the definition of errorless average case compresses. So what I'm going to show you is that by using this instant checker, we can convert Heuristics algorithm for L, D prime for some distribution D prime can be converted into errorless average case polynomial time algorithm for L, D. So in order to prove this, let Q be the query distribution of the non-adaptive instant checker C. Now we can define D prime to be Q composed with D, and then we take error-prone heuristic A for the distribution problem L, D prime. Now we can describe errorless average case algorithm for L, D, which we call B. So the definition of the errorless heuristic B is as follows. Given an input X, you simulate the checker on input X. And if the checker makes a query, then we answer it by using the error-prone heuristic A. Here we take a sufficiently large parameter K so that the error-prone heuristic schemes are correct with high probability. Now I'm going to explain why this is an errorless heuristic briefly. The reason why B is correct with high probability follows from the completeness of the instant checker. By using a union bound, we can guarantee that the probability that all the queries that are produced by the checker can be answered correctly by using the error-prone heuristic A. So that's why B is correct with high probability. Similarly, we can prove that B is errorless by using this soundness condition. So this is why we can get the reduction from errorless compressivity to error-prone average case compressivity by using instant checker. To conclude this talk, we have identified the connection between errorless versus error-prone average case compressives and instant checkers. There are a lot of interesting open questions about this paper. One important open question is whether we can construct an average BPP/poly instant checker for NP complete problems. If we can do that, we can construct errorless to error-prone reductions. Alternatively, we can try to give a negative evidence against this. What's most related to this question is the work by Bogdan and Trevisan, who showed that there is no non-adaptive worst case average case reduction unless pH collapses. our notion of errorless-to-error-prone reduction is a weaker notion. So if we can extend their result to our setting, we can give a negative answer to the main question. Thank you for listening.